Hey, hello everyone. My name is Keyan Li. I'm from the marketing group. So today I'll be presenting my job market paper, Targeted Marketing with Large Batches. So this is a paper on targeted marketing, which means that firms want to send different marketing actions to different types of customers. I don't need to convince this audience that targeting is everywhere in our daily life and all sorts of business context. But how does targeting work? Let us all imagine that we are in the marketing department of Costco, a large wholesale membership club. So every year, Costco conducts marketing campaigns for their customers. We have a large number of marketing actions we can use, for example, emails and direct mails. We're also able to, based on our available customer data, profile our customers. For example, we could have some low-profile graduate students and some high-profile celebrities. And so the goal here is to, for each of the customer, identify the action that leads to the best performance. So that could mean that we might want to send emails to one type of customer and direct mails to another type of customer. So this type of correspondence is what we are calling a targeting policy. So how does a firm actually train or construct such a targeting policy? Well, the answer is actually quite simple, right? Using data. Based on the past customer data, we're able to build a machine learning model that informs the firm which is the marketing action that leads to the highest performance for each of the customer. And so then we're able to put together those insights to construct a pretty concrete targeting policy. But in practice, targeting is never a one-shot game. And firms, for example, Costco here, we always need to conduct marketing campaigns every once in a while, which introduce an adaptive learning problem. What does it mean here? We can consider this timeline. So suppose we can start from a current policy, which is trained based on the past customer data. And our problem today in the current campaign is to make decisions on all of the customers in the current campaign to make personalized action assignments. And so this adaptive learning here means that when we are making those decisions, of course, we can directly apply this current policy to the customer, but we might also have an alternative consideration here. That is, we hope to be able to better predict the behaviors of our customers in reaction to the assigned action. And so that with this new type of new piece of information, after this current campaign, we're able to update our policy. And so in the future marketing campaigns, we could have a hopefully better policy to use and improve the targeting performance. And so this means that when we are solve this problem today, apart from directly following this current policy, we might also want to bank some customers for experimentation. The research question we try to answer in our paper is to come up with a decision-making device to automate this process along this type of timeline. And so there seems to be a large body of literature in both marketing and computer science trying to construct solutions to solve similar types of adaptive learning problems. But in our paper, we want to argue that it's actually infeasible to directly apply those existing solutions to solve our targeted marketing problem here that Costco and many other firms also face. To see this, let's first consider a classic adaptive learning setting. In this classic setting, things are in real time. And so those classic algorithms will optimize action for one individual at a time, sequentially. To visualize this process, we can take a look at this timeline here, starting from the current policy. Each time, one customer will arrive, and then we can assign action, the customer will respond, and we can use that information to update our policy before the next customer arrives. And then we can repeat this process going forward. Be more specific about the related research domains here, I'm merely referring to the contextual bandit algorithms as well as Bayesian optimization. At this point, you might already realize that there is kind of a gap between this real-time learning setting and Costco's marketing practice. That is, for Costco, each of the marketing campaigns we typically conducted with a large number of customers. Right? So our ideal algorithm, we will have to optimize action for a large batch of customers simultaneously. So this type of batch learning setting is actually quite common in business practice. For example, you will see a lot of firms having the same difficulty to implement this quite sophisticated and expensive infrastructure. And so they oftentimes do not do real-time learning. Instead, they process information every once in a while, or even conduct marketing campaigns with in batches. And so there are some other reasons. For example, firms also face seasonal demand. This is very common during holiday seasons, and there's often a high fixed cost associated with running a campaign, and also a big delay in terms of observing the outcomes. So to contrast the difference, we can see the two visualizations here, and as you can see, the only difference here is that instead of having one customer, we're having a large number of customers in each time, and we need to make action assignments for entire batch of customers, and we're not going to get any response from any one of these customers until we finish the entire assignments. So you might wonder, why do we care? Why do we care about this difference? In the upcoming slides, I'm going to show you an important implication that we need to understand in order to solve our problem that is raised due to this difference. So I'm hoping to explain this implication using a very simple example. So consider those 3 customers being 3 of the customers in today's batch. And our problem today is to make personalized action assignment decisions to each one of those 3 customers. As you can directly see from their profiles, they're different customers, however, they are very similar. And so when we are making a decision, we can either directly exploit the current policy by following it, or explore to experiment and try to get some different types of information from those customers. And starting from the classic adaptive learning solution. And this classic solution will always rely on the latest, the most recent estimated targeting policy when they're making decisions. And because we know that we're not going to get any response halfway during our assignment, we have to wait until the end of assignment. And so it's very likely that this classic solution will recommend the same action because those 3 customers are very similar, and we're basically referring to the same policy when we're making decisions. So what is the problem? If we focus on the 3rd customer here, remember the 3rd customer is similar to the other 2 customers. And although at this point we have not heard back from any of them, we still anticipate that the information we're going to get from the 3rd customer will be duplicating with some of the information we will get from the other 2 customers. And this information duplication will kind of diminish the combined value of exploring all 3 customers, and so we might be better off to only explore the first 2 customers and exploit the 3rd customer. And this is what we are referring to as an information externality, which is also the key insight of this paper. It means that the unique information contributed by any one customer will depend on what type of information, what kind of action assignments you give to all the other similar customers to that one customer in the same period. So in the rest of my talk, I'm going to give you some very high-level intuitions around the decision model and the algorithm we use to solve this problem with that information externality challenge. So let's take a very quick look at our model. In the paper, we built a decision theory model to directly trade off the opportunity cost of information and the expected value of information for any given customer action pair in the hope to be able to deterministically get the action assignments for each customer. So the challenging part here is the expected value of information, because this is where the externalities come into the picture, and we need to get only the incremental value from each customer. In our solution, we basically rely on a nice result from our model, which implies that we're able to quantify those incremental information as long as we fully specify the action assignments of all the customers, essentially the similar customers, in the same period. There's also another important takeaway or insight from the model, which is that this problem itself is a combinatorial problem. So that means we're not able to individually optimize each customer's action. We have to do a joint action assignments. So in our model, customers are no longer separable in this big problem. So with that, I'm going to also talk about, in a very high level, our algorithm and our effort to validate this algorithm. So our algorithm has 2 parts, an estimation part and an optimization part. In our estimation part, the key challenge is that we need to quantify not just the mean, but also the high-level moments and essentially the variance of any predictions given by the current estimates of the targeting function at any with any combination of feature values. This is a quite challenging problem because we typically don't get a pointwise uncertainty estimates from any prediction model. To solve this challenge, we use a Gaussian process-based framework to build the entire targeting framework. And this is also our part in the algorithm because we're hoping to get all of our assignments based on our decision model. And with this framework, we're able to very flexibly and efficiently find out all the numerical solutions without having to solve this model in its closed form. And a little bit about the optimization step of our algorithm. Of course, the key challenge here is to solve this joint optimization that we just talked about. This is also a very hard problem, and to solve it, we propose to use a clustering approximation to break down this big, giant, single joint optimization problem into many smaller joint optimization problems. And we solve each smaller optimization problem by focusing on still the most important part of the information externalities, but this also largely simplify the whole computational complexity. In the effort to validate our algorithm, we used some past experiment data, and we run a contest competition between our algorithm and the benchmark policies. And as you can see here, our algorithm outperforms the other benchmark policies. In light of time, I'm going to very quickly wrap up the talk and by concluding a few of the key takeaways from the paper. So 2 contributions of this paper. First one is we identify this information externality challenge in this new batch targeting problem. And the second one is we propose a new profitable solution to solve this problem with this challenge. And finally, I want to talk about something more general than just the targeted marketing. So actually, this point about information externality, generalize beyond just the targeted marketing, which kind of nicely fit into my current research program, which is on the current cost-effective experiment. The message is that when we think about firms running experiments, this happens all the time. For example, if you think about firms running A/B tests, they do a lot of similar A/B tests, correlated A/B tests around the same time and also over time as well. And so this information externality also arises there. It's because all of those A/B tests, all of those small experiments, they share some correlated information. And so to avoid those information externalities, to avoid introducing those hidden opportunity costs, at least some level of information coordination will be needed. All right, thank you very much.